So here's my momentum tutorial. Questions from the review number 14. That one there. Clip. This one, Troy? Okay. Collision. Momentum. So I think the first thing that I would do is go the sum of all the momentum before the collision equals the sum of all the momentum after the collision. Before the collision, what was moving? Mass 1, mass 2, or both? So I'm going to have momentum of mass 1 initial. After the collision, what's moving? Mass 1, mass 2, or both? Stuck together? Oh, I got to list them separately then. Mass 1 final and mass 2 final. Angles? Yeah, see, if not, I can just go to numbers and cross multiply and do a little bit of arithmetic. But, okay, angles. Picture, dull. Here's mass 1, incoming. Looks like it's due east or right. They didn't give me a northeast, so to the right. And its momentum is mass times velocity. I can't just put the velocity on here. I got to put momentum on here. Momentum is mass times velocity. That I can do in my head. Half of 2.4. The initial momentum is 1.2 to the right. Equals. Afterwards, my momentum looks like this. Momentum 1 final is that way, where this is a 30-degree angle, and momentum is what times what? So I got the velocity, here's the mass. I think here the final momentum is 0.9 plus the mystery momentum, and I'll call it momentum 2 final. And the angle that they want me to find is that one there. I'll see where that ends up appearing in my triangle. Oh, how do I add two vectors together? Draw them tip to tail. So I will. Here's the nice thing. When I draw these tip to tail, I know the answer. It's supposed to give me a triangle exactly horizontally. That's how I know how to draw my vector triangle. I know that if I go 0.9 plus mystery final momentum, it has to give me an answer of exactly horizontal 1.2. Where this angle here is 30 degrees. Sorry, I'm chewing. How can I solve this? SOHCAHTOA? Cosine law. Momentum 2 final squared equals 0.9 squared plus 1.2 squared minus 2 times 0.9 times 1.2 cosine of 30. And then don't forget to square root. The final momentum and then square root. You get 1.38449? Yeah? I'll go 1.3845. I'm not done. This is the momentum, Justin. Justin, what does the question want me to find? Not the final momentum. What does it want me to find? speed and direction, velocity, magnitude, speed, direction, theta, velocity. If I know the momentum, how can I figure out the velocity? Yeah, momentum is mass times velocity. So, and divide by which mass, Ian? Mass number 2. That's why you'll notice I've also gotten way more careful in my labeling and notation. There's lots of room to make sloppy mistakes here, as well as the math is pretty heavy. I agree. So Gordon, I'll get this. Velocity 2 final is going to be 1.3845 all divided by, is that a 0.3? Yeah. All divided by 0.3. I get a velocity of 4.6 meters per second. And then I need the at, the direction. Now, sorry? Oh, am I way off in radians? Oh, don't do that. I am in radians. Someone should have spoken up. How about you get this? You get 0.6159? Ah. I wish I'd done that on purpose because that would have been a good teaching moment, but I just had a brain cramp. 0.6159. Didn't I say, though, when I wrote this down, is that right? Did anybody else get that and nobody said anything? Oh, you were also in radians. Yeah, okay. All my block D math 12s. Yeah, it looks fine. Okay. Tells me how much homework you did in math 12. And then divide by 0.3. Divide by 0.3. How about 2.05? Is that right? 2.05 meters per second at theta. Now, it's going to be, looking at the diagram, that angle there. Brandon, see the Z? That angle. And to find theta, I can use the sine law. It's going to be the sine of the mystery angle divided by what's across from it, Dylan, which is 0.9. And that equals the sine of the angle that I do know, 30, divided by the side that I know across from it, which I didn't used to know, but now I know is 0.6159. I'll get sine theta equals 0.9 sine 30 all over 0.6159. I am in degrees now. 0.9 sine 30 divided by 0.6159. I get that decimal. That's the sine of theta. How can I find theta? Inverse sine of that. And you don't need to worry in Physics 12 about the cast rule or anything like that, because we're staying always in Physics 12 in the top half of the circle, for those of you that are in Math 12. So our inverse will work. We're only finding one answer anyways. 47 degrees at 47 degrees. You could either say below the horizontal. Yeah, I would probably go with north, east, south, and west, and I would call it south of east. That is absolutely a question very similar to what you'll see on the test. Okay. Seven. almost done here. Okay. Next. For those of you McDonald's boys who got here late, I said I can print this up for you when you guys are done, or you can write stuff down. Sorry? Okay. 33. What do I want? In this case, this is a bit different, Brandon. I know the final momentum. What do I want the final momentum to be? What word tells me 0? I think you just echoed somebody else. Stationary. Why does that help? Momentum is what times what? So if you're stationary, what's your velocity? And since momentum is mass times 0, what's your momentum? So this is a bit different now. They're telling me the final momentum is 0. In fact, here's what I think, Brandon. I think if I add this momentum to this momentum vectorially, this will be the same magnitude, opposite direction. That's what's going to give me the 0. So what I'm going to do is take these two and add them together. How will I add them together? So I'm going to go like this. 4 times 8.3, 33.2, and add that to, oh, I could do that in my head, 2 times 7.2, mass times velocity, 14.4. Now, my scale here is terrible. Really, this is half as big as that. Really, I should be drawing a triangle probably like that, okay, with twice as long. If you can fit it on your diagram, great. How big is this guy? What do I want the final momentum to be? End up back where you started from. That's going to be R. Now, thankfully, this question's not too bad. Are they wanting theta? Are they wanting the direction, or do they just want the magnitude? Oh, magnitude. And they don't even want the velocity. They just want the momentum. So how can I find the magnitude of that? Pythagoras. Darn right. 14.4 squared plus 33.2 squared square root. Whoop. Square root. 36.2. C. How else could I ask this? Instead of asking the magnitude, I could have just said at what angle, what direction. Okay, so you wouldn't do the Pythagoras, you'd do the trig. I think tangent would get you an angle. Or, if I wanted to make a good written question, tell you the mass of object R and find the velocity. Okay. And by the way, this is the reverse of an explosion. In an explosion, we had everything traveling away from the center. Can you see all three of these are traveling towards the center, which is also another way of saying you're going to get a final momentum of 0. In an explosion, you knew your initial momentum was 0 because you knew everything was starting out with a velocity of 0. Any others? 34. Am I going to end up doing all these angle ones for you guys? Are you wanting me to do this, or you just want to see if you're right? Or yeah, okay. I'm just a little worried I'll end up doing all of the angle ones. Hopefully there's more angle ones on your review, because I don't want to do them all for you, but okay. Clip. This is identical to the one you asked me earlier, kiddo. No, it's not. Yeah. Two objects stuck together, but it's going to be the same idea. I'm going to start out saying, hey, collision, yeah, momentum. The only difference now is when I ask, before the collision, what was moving? Mass 1, mass 2, or both? Both. Stuck together? Then list them separately. After the collision, what was moving mass 1, mass 2, or both? Stuck together? Angles? Are there angles? Draw a little picture. If not, Dylan, you can just go MV, MV, M both V, and cross multiply and subtract and just solve it like a regular equation. Angles? Oh, vector. V1 looks like this. Plus, oh, magnitude. Can someone go mass times velocity for me, please? 4.2 times 1.8. 7.56. Not rounded off, carry out. Oh, yeah. Okay. And mass 2 is coming in like this. Mystery angle, but we know, oh, and mystery velocity. So I'll just call it momentum 2 initial, don't know, equals, I do know by a rare fluke that momentum final is dead horizontal, which is convenient. And now the velocity is 2.3. What mass am I going to use here? Both. So I'm going to go 4.2 times 1.3. Sorry, times plus 4.2 plus 1.3 mass times velocity. That's got a momentum of 12.65. Is this a final momentum of 0? No. So is this a triangle where you come back to where you started from? Nuh-uh. Added together tip to tail. 7.56. Mystery. Oh, not final, Mr. Dewick. Initial. 12.65. Where's the 30 degrees going to end up? Bottom, top left, or top right? Top left is correct. Look up. I would do this, right? How big is that? 30. See the Z? $30. Sorry? Okay, that's how I would draw it. Then what? Cosine law. Don't forget to square root. How do I find the velocity? Divide by mass 2. Angle. Angle I would use would be this one right. Oh, good gosh, Mr. Dewick. Angle I would use would be this one right here, which is that one right there. So I'll find the magnitude of that angle, but I'll put it here, and that would be north of east. I think. I really can't do those without drawing a compass. Well, it's saying find that angle, but what direction is this thing traveling? Is it traveling south of west, or which way is it traveling? It's traveling north of east. So you always go back to where your vector is starting from. That's where your direction comes from. Okay? That was quick. Okay. I'm going to try and upload this if all goes well. If I do, I'll email you guys. If it doesn't work, then I won't. What number was that, Troy? 34? So why don't I be clever and just do this? Right? So there's the same idea. $40 or 40? 40? 40? Ugh. Okay. Well, it's a collision, so sure. Okay. Um, First thing I did to get a good picture is I wrote down, I'm going to assume the incoming nucleus is moving due east because that's the way that most of our collisions have worked. We had something move to the right. I said, collision, momentum. Okay with that? What's moving before the collision? Mass 1, mass 2, or both? Just mass 1. So I crossed out mass 2. After the collision, both are moving. And then I drew a picture. I said, you know what? It's going to look something like that, where that's right there is a 90-degree angle. How will I add those two together? Draw them. Tip to tail. Tip to tail. Oh, mass times velocity. And the incoming one was due east, mass times velocity. This one was kind of nice because no sine law, cosine law. I can actually use good old right angle trig. I used, what did I use? I found theta by going shift sine, which was unusual. Often we use tangent. And I found this by going Pythagoras. That squared minus that squared equals that squared square root. Right? That squared equals hypotenuse squared minus the short side squared. So this one wasn't as bad. The reason initially I groaned, Troy, this would be an example of, because we have right angles, because the masses are identical, I think here you would find kinetic energy was conserved. The amount of kinetic energy before the collision does equal the amount of kinetic energy after the collision. This is a perfectly elastic collision. I think. Let me just double check. Before the collision, we have a half mv squared. After the collision, I have a half times m times 24 squared plus a half times m times 10 squared. Yep. Okay. So for what it's worth, if you happen to have a 90-degree angle and your masses are identical, if you actually sit and do the trig, you'll find, oh, because it's Pythagoras and SOHCAHTOA, the m's cancel, and I do get, well, Pythagoras in disguise. v1 squared equals v2 squared plus v3 squared. It's actually c squared equals a squared plus b squared in disguise. Big deal. I didn't do a big emphasis on perfectly elastic collisions. You do need to know what is conserved. Momentum, yes or no? Yes. Total energy, yes or no? Kinetic energy, yes or no? I'm taught always. No. Rarely. Only in rare, specific, special collisions. Okay. Next. Okay, then look up. Let's do a bunch very quickly. Boom, boom, boom. Number 9 here. This is an old review, so that's why I don't have a copy for you. It says, what is the change in the momentum of an object of mass, blah, 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 if a constant unbalanced force of that big acts on it for that. So change in momentum. What's another word for change in momentum? Impulse. Am I going to use final minus initial change in momentum here? No. No. So you might want your formula sheet out. If you haven't already, there's an equation for impulse. Now, impulse is another word for what, Miguel? Change momentum, which is always final minus initial. But impulse on your formula sheet, change in momentum, delta P, is also what, Zach, on the formula sheet? Force times change in time. How do I know without having to think about it too hard that's the one they want me to use? Look at the question. Do they give you a force? Do they give you a time? In fact, the answer here is going to be 2.9 times 4.7. They didn't even need to give me the mass. That's just to throw me off. 2.9 times 4.7. Okay. By the way, I skipped number 1. Number 1 is perfectly elastic, which means I know it's a right angle and I know the masses are identical, but that's overkill. Number 5, an incident ball A strikes a stationary target ball B. The momentum vector of the incident ball before and after the collision are shown in the above diagram. Whoop. So there we go. I need that. Which vector represents the momentum of the target ball after the collision? Let's see. The momentum vector of the incident ball, so that means the first moving one. So I think I need to visualize this. I need to draw this just a little bit. So I'm actually going to close it in this program. And I'm going to open this up in PDF Annotator so I can write on this file. I think. Okay. We a little tired? Okay. So here's what we have. We're envisioning some kind of a sphere coming in. There's another sphere right here. So the first one bounces off this way. Which way is this guy going to bounce? Just think about it. Which way is it going to bounce if the first one bounces up high and to the right? I'm pretty sure. Got to be A. Is that right, Mr. Dewick? Let's find out. All momentum answers. A. Pardon me? On the old provincials, they used to be 2 hours long, and the provincials were 120 marks, 60 multiple choice, 30 multiple choice, 2 minutes each, and 60 marks worth, 60 minutes worth of written. It was actually a nice little balance. The physics guys had it going good. And so the person who set these up, who I borrowed these from, Mr. Kreitch over at SRT, he would actually time himself how long it should take maximum if you're pacing yourself to do it. So you'll see next to his, shouldn't take you any longer than 2 minutes. If it does, you're in trouble. You're not going to finish the provincial. Because back then you only had 2 hours, not 3. They were, fussier back then. Number 3, a stationary life raft is carrying 2 survivors with masses of 55 and 72 kilograms respectively. They dive off the raft at the same instant. Oh, before they dive, what's the momentum of the 2 people and the raft included? I heard it. Sorry, I heard it. Yeah? 0. This is an explosion. It's a slow explosion. But when you do this question, you would go, okay, my initial momentum is 0. First person, second person raft. How does 0 show up in a vector triangle? A triangle that does what? Comes back to where it started from. So I drew a little picture here. Absolute value, I was using that when I first started teaching Physics 12. That's the symbol for magnitude only, and I was really, really fussy on that. I've eased up on that a little bit, but for what it's worth, that just means magnitude only. And this was a right angle, woohoo, straight Pythagoras. And they wanted the speed and the direction of the raft, so I knew the mass. Once I found the momentum, 387.31, I could then divide by the mass. That gave me the velocity, and it was tangent, I think, to find the angle south of west. Another collision at an angle. By the way, if you have a question from the review, just interrupt, but I'm just kind of trying to go through a bunch of stuff. Here's another collision at an angle, number 6. Toy car, mass moving east, collides, and they lock together, so afterwards it'd be a momentum of both final. Means divide by the mass of both to find the velocity. This one here almost certainly, oh, Due north, due east, probably don't need sine law, cosine law. You'll probably end up with a lovely SOHCAHTOA triangle, and then you'll have to find how many degrees east of north. All they want is the actual angle. Number 7. Which vector shows the direction of the change in momentum? What's change in anything? Okay, so the change in momentum is going to be final minus initial. Now, they haven't given me any numbers, but I definitely know the final looks like that. How do I subtract a vector? Add the opposite. So normally I would go minus initial, except I'm going to add. Where's the eraser here? There it is. Where's the pen here? I haven't used this for a while. There it is. I'm going to add the opposite. I'm going to add those two. How will I add those two? And if I'm seeing this correctly, I think I end up with the change in momentum being straight up, which makes sense to me because I don't think the ball slowed. If we ignore friction, I don't think the ball slowed down horizontally at all. I think all that happened was it changed its vertical direction. It got pushed up. Saw a cannon there, Mr. Duke. Yeah, we've done a bunch like that. Object A splits in two. That's an explosion. We've done a bunch like that. Done a bunch of those. Another angle. So here's one where we don't have angles. Number 2. A 4,000 kilogram space vehicle consists of a 2,500 kilogram main capsule and a 1,500 kilogram probe. The space vehicle is traveling at 120 meters per second when it explodes. Explosion, momentum. Now, in this case, they want the speed of the main capsule after the explosion. I would still start out the sum of the initial momentum equals the sum of the final momentum. But this time, even though there's an explosion, thanks, Gord, even though there's an explosion, Zach, my initial momentum is not 0. Before the explosion, can you see it's mass times velocity? Before the explosion, angles? Straight, adding, subtracting, cross multiplying. Let to the left be negative and to the right be positive. So momentum is mass, 2,500 and 1,500, 4,000, times velocity. That's my initial momentum. After the explosion, what's moving? Mass 1, mass 2, or both? Stuck together? So I'll have mass 1 V final plus mass 2 V final, where mass 2 is 1,500, and what's V final? 140. Positive or negative 140? Because I let to the right over here be positive, so I would replace this with 1,500 times 140. And could you solve for the speed? You know mass 1 is 2,500, right? Ooh. That's cool. So solve for the speed. What if you got a negative answer? What would that tell you? Which way is the main capsule moving? To the left. The explosion was so big that it sent the main capsule backwards. This is actually the idea behind a booster rocket. Ideally, what you want is this guy's momentum to be 0 or even backwards, because that'll impart more impulse forwards to this guy. So in a booster rocket, the idea is the probe goes taking off. And it is a controlled, careful explosion. Part B says, what's the magnitude of the impulse? It's another word for impulse. Yeah, and here I'm definitely not using force change in time. I'm going to go final minus initial. Final is probe. Final is mass times velocity, to positive to the right, minus initial. This time, don't look at both of them, just this mass times the velocity. So it would just be 1,500 times 140 minus 1,500 times 120, whatever the heck that was. That's your change in that momentum. That's your impulse. How else could they change this? Oh, if the explosion lasts for 0.03 of a second, what was the average force acting on the probe? That's where you would use the F delta T once you found this answer. Oh, here's a right to explain. Define impulse. Define impulse for me. Change in momentum. And I'd probably put in brackets. What do you think I put in brackets? What's change in anything? I probably put in brackets momentum final minus momentum initial. And then it says explain why the impulse on the probe is equal in magnitude to the impulse on the main capsule. Momentum is conserved. Whatever momentum this guy gained, this guy lost. That's why they said equal in magnitude, but opposite in direction. So, probably answer it that way. Momentum is conserved. In fact, you know what? I would probably, because I have numbers here, I'd probably prove it mathematically. I would actually crunch the numbers. I would show, since I just figured out the impulse in part B, I would calculate the impulse here, and I would show that this was the same answer, but negative. I could probably do a fancy algebraic expression proof as well, but eh. Yo. This one here? I don't know. I don't remember what they wanted on the provincial for this one. This was from... don't know when this one was from. Oh, it's on the review? On yours as well? Yeah. What did I say in the back? What did I say in the back for answers? Because I think what I did there is I copied it. If it's digitized, I would have just cut and pasted their answer from the provincial exam. No, for the explanation here. So that's me lifting that verbatim from the provincial exam answer key. I'd probably, if you said momentum is conserved, I think I'd take that. The only concern I would have is, do you know what the word conserved means, or are you just parroting something that you've memorized? Right? So if I was hedging my bets, I'd probably just show it. It'd be easy enough to go mass times velocity, or to go impulse for the capsule as well, final minus initial, and show they're the same number but opposite magnitude. Hey, another one of those. This one was a bit trickier because they didn't give you any velocities. Instead, they told you how far it traveled and how much time. So you actually had to calculate this velocity first. That was overkill, I thought. Puck sliding, to the east, collides, they stick together. Oh, the only twist here, the reason this is a scholarship question is, instead of asking you to find the final velocity of the 2 kilogram puck, what do they ask you to find instead? Change momentum. What's change in anything? Final minus initial. But it would be subtracting 2 vectors. You'd have to do trig cosine. This was a 10-mark scholarship question. I won't give you one this tough, but Dylan, you'd have to do a 10-mark, a triangle question like I did with Troy to first of all find the final velocity and then do a final minus initial vector triangle to find the change in momentum. A little overkill in my mind. Yes, I sent it out quite some time ago. Because you were colliding things at angles? Yes, which is why I sent it out after the energy test. Yes, where you're causing things to bank and grate off each other, much like the pictures of many of these collisions, kind of like that. You were sort of doing that.
I thought that was for the last one.
No,
No?
no.
Well, I sent it to you, right?
Probably. Well, you sent me a cell phone one.
Yeah, I wasn't there.
See, because you sent, we wrote the test before Christmas. Why would I have you write a test and then decide whether or not you want to do the bonus assignment?
I don't know. You got my email, and you know what email, that's all.
Well, I can't find very many, if any. If I could, I would. Hey, number 2 here, explosion. Okay? What's the momentum right now? Boom! What's the momentum afterwards? Still 0. It's going to be a little bit weird. It's going to be a closed triangle. I don't think this is going to be a lovely right angle triangle because I see one at an angle. There is going to be an explosion on your test, but I'm pretty sure I kept it a lovely right angle. Now, because I kept it a right angle, it means I also asked a part B. I'll let you think about what kind of part Bs I might be able to ask. You've kind of seen some hints along the way today, some of the part Bs that you've seen in some of these written questions. Something along those lines, maybe. Okay? Ballistic pendulum. This one is an old scholarship question. I expect you to handle the concept of this one, Justin, but the reason this one is so tough is, first of all, they're asking you to find the speed of the bullet after the collision, and they don't tell you how high this went. Instead, they just gave you the angle, and you know this is 1.4. You have to figure out 1.4 and an angle of 22 degrees. You have to figure out that height there. You got to do some trig. This is a much tougher question than I'm going to give you. But hopefully you understand the idea of two things colliding in a nice straight line, and then with this change in height, change in energy, use conservation of energy. Number 7. On the provincial and on some of my tests, I've tried to, in the notes whenever possible, remember I think we did a baseball, a bicycle rider, and a car, and we tried to figure out what would hurt, what would injure, and what would kill. Right? I think we called it pain, injury, and death. Okay? So what would the momentum be of a car? Well, momentum is what times what? Mass times velocity. Now, city speed limit. What is city speed limit? 50k meters per second, please. 13.8. What would a good mass of a car be? 100? Does a car weigh 100 kilograms? 2,000 pounds. Get away from pounds. Kilos. Look at your numbers here. Leslie, let's try 1,000-ish. So go that number, mass times velocity, guess of about 1,000. Which of those answers looks more reasonable for the momentum of a car? A, B, C, or D? I think B, right? A, if I divide that by the velocity, 3.6, I get a car that weighs like, what, 15 or 20 kilos? That's, no. I think C, if you divide that by, what was the velocity? 13.6? 13, what's 100,000 divided by 13? See, that's a car that weighs 10,000 kilograms. That's 10 tons. Do vehicles weigh 10 tons? I'm not even sure those great big, huge, huge mining dump trucks with the tires that are higher than this ceiling weigh that much. So it's got to be B. Hey, which of those would probably be the best representation of the momentum of a locomotive? Like a full train. I think D. Because there I would think, although not many cars weigh 10 tons. I think probably 2 train cars would easily weigh 10 tons. Probably 1 train car might weigh close to 10 tons. So if you had a train with several cars, yeah, D or higher. Okay. Number 8. What's this asking you to find? Number 8 here. What's this asking you to find? Number 8. Here. Sorry. The one that I showed the entire question for, as opposed to this number 8 where I didn't even bother scrolling it up all the way. Number 8, this one here, what are they asking you to find? It's a good point, Justin. What are they asking you to find? Impulse. Am I going to use force times change in time here? How do I know I'm not going to use F delta T? Okay, Vital, you got your formula sheet in front of you. There's two ways to do impulse. I'll say this again. What's another word for impulse, Vitali? No. What's another word for impulse, Justin? Change in momentum. It implies an operation. changing. You can't just say momentum. I'll totally mark that wrong, and you'll have the wrong concept. Impulse is changing, which means you always need what's changing anything. So one way of doing this would be to go momentum final minus momentum initial. But there's also, Zach, can you show them your formula sheet, please? There's also an equation. What's the equation? Okay, so here's my question. Ready, Vitaly? How do I know they don't want me to use that equation? There's no time. What else is not here? Force. And does it look like they've given me a final and an initial velocity? Yes. Is there a rebound? Then you'd better let one be positive and one be negative. Because I guarantee one of these answers is if you just go final minus initial and you go that times 25 minus that times 15. You can't do that because you've let them both be in the same direction. And it definitely says the final velocity is west and the initial velocity is east. So I would probably let either to the right be positive and to the left be negative, or vice versa. You gotta do one of those. Okay? And then to figure out the direction, if you let east be positive and you get a positive answer, the direction is east. If you let east be negative and you get a positive answer, the direction is west. In other words, you look at what you let be positive and you look at the answer that you got. If they're in the same, if they're both the same sign, they're in the same direction. Vitaly, look at number 7, the first number 7, this number 7. Read it to yourself, please. Okay? I'm going to use impulse here too. Okay, here's what I would do. I would say change in momentum impulse is force change in time. And since they mentioned time and they're talking about force, how would I get the force by itself? Divide by time. A problem. I'll do that last. First, I'll figure this out. How can I figure this out? Final, mass times velocity, minus initial, mass times velocity. Opposite direction, I better let one of them be what and one of them be what? One of them be positive, one of them be negative. And then I'll go final minus initial, and then I'll divide by time. You'll get a negative force as an answer. All that's telling you is the force is in the opposite direction of your initial velocity, which makes sense because if the ball hit the wall, it had to come to a stop, which is applying a force that way. And if it goes this way, it must have applied an even bigger force this way to get it to go that way too. Right? So the physics behind a simple tennis ball hitting the wall, right? Wonderful. Change in momentum equation. Nice job. Let's do it. Hit the paper. I knew it wasn't going to bounce properly. Right underneath my desk, of course. Okay. The physics of hitting the wall with a tennis ball. Great example of impulse. It's also nice because for a split second, everything's linear. If we ignore that, it's going to drop as soon as gravity takes it. We'll be in our magic physics world. The math nice and simple. We won't worry about the vectors. Or even better, if I do want it to definitely be linear, that, right? Which way did the ground apply a force? Upwards, if you know the time collision. It applies a fair bit of force because it has to first of all bring it to a stop, change its momentum to 0, and then give it even more impulse to get it to go back up. So that one would be linear. What would require a bigger change in momentum? If this was flat and just came to a stop, or if this was all pumped up and bounced back up, what requires a bigger change in momentum? Huh? Well, let me ask you a different question. So let's go back to Vitaly, because he's still. Oh, I thought you were wearing a Russian hockey team jersey. Sort of Canadians, almost as offensive. No, more offensive. Vitaly, you're walking along the street in downtown Vancouver next to a high-rise, and somebody knocks a flower pot off of their window from the 4th story, and it lands on your head. What would do more damage if it landed on your head and came to a stop, or if it landed on your head and bounced all the way back up to the window so you could grab it again? What would hurt more? The bounce. So where would your head apply a bigger impulse? where would your head apply a bigger impulse then? The bounce. Because you've got to bring its momentum to a stop and give it all the momentum going up. Okay? It's soccer players. Who am I, soccer? Or baseball. Okay? Bunt. Very easy on your hands, as long as it doesn't hit your fingers. Rarely do you see a batter after a bunt get that stinging feeling. Hit, you really feel it in your hands because you're having to apply a way bigger force, a way bigger impulse. Okay, I've gone on a bit of a rant there. That's energy, actually. That's energy. Oh, here, number 10. Two cars collide head-on and come to a complete stop immediately after the collision. Which of the following is correct? Total momentum. Conserved or not conserved? Always. Total energy. Always. Kinetic energy. Not always. And in this case, can't be. Because what's the final kinetic energy? 0. What was my initial? Not 0, otherwise you can't have a car accident. Okay? Anyways, the answer here, A. Done a bunch of these. You can see they start to get kind of repetitive. Okay? So there's either going to be two guys coming in and sticking together and moving off in a nice straight line, or one guy coming in on a nice straight line and then they split apart. But you're going to have one of them in a nice straight line. That's what helps you draw the vector triangle. Front of an automobile is designed to crumple in a collision in order to reduce the injury to the occupants using principles of physics. Tell me what the principles of physics are that help this work. Why does this improve safety? Ian. Yep. In fact, it's exactly the same as my baseball bat. There it is. I'm sure in each one of your classes, I think I would have held a ruler and this, which have almost identical masses, and I would have picked somebody and I would have said, you're going to get hit in the head. What do you want to get hit by? It's going to be the same mass. Final velocity is going to be 0, so it's going to be the same change in momentum. What can we do to lessen the force? Lengthen the time of impact. Crumple zones. And I showed you guys the smart car crash video, yes? And then I went on a bit of a rant where I said it's even the passenger compartment is actually the hypotenuse of the triangle. If you look at the smart car from the side, it's tilted up because they have to somehow give you a longer crumple zone, and they don't have much room to work with, Dylan, in a smart car. So what they did is they tilted it up like that because there's a hypotenuse longer than that. There's your extra crumple zone. You actually crumple downwards a little bit. There's a nice little bit of engineering there. Very clever. And now you're going, oh, that's why it looks like from the side, those smart cars, that's why they look like that. Yes. They designed the passenger compartment like that deliberately. Pardon me? So, I've done more from my old review. Are there any more from the new review where you've been going now, hey, I have some more questions? Remember, the answer key is online, so if you're stuck, it's all there. Okay. Leslie, I've been ignoring you. You have any questions at all? Or hopefully that helped a little bit. I'm going to go like this. Nope, I'm going to go like this. Right click.